Okay, so let's talk about objects on an incline. When you have an object on an incline, the forces are going to be at angles, and so our goal is to make it such that we have the fewest amount of forces that we would have to break up. One key thing about when you're looking at how to break up forces on an incline or how to set your coordinate system is that you always want to make your coordinate system such that acceleration is along one of your axes. So you want to make the direction of acceleration along one of the axes. And this makes it such that you do not have to break up your acceleration into components. You're just breaking up forces into components. So it's going to be a little different in terms of what we're used to breaking up. Normally we're used to breaking up things like tension, etc. And this time we're going to be breaking up, mainly we're going to be breaking weight. So let's go ahead and see that. So let's say we've got an object on an incline. So for example, if we have an object accelerating down a ramp, if you were to look at the forces on this, we definitely are going to have a weight that is going down. The ramp or the incline is exerting a normal force because there's somewhat of a surface being exerted, or support force that's being exerted. And you have a friction because our object is definitely moving down the ramp. So if this is our direction of acceleration, friction would oppose that. And for something that's just accelerating down a ramp, there's nothing that's actually pushing. There's no F push that's forcing it down the ramp. It's just the fact that a portion of the weight is along that direction, and that's what's causing it to accelerate down the ramp. So if you look at this, the key that we just wrote up was the idea that we want to make sure that our acceleration is along one of our axes. And so that means that our axis system is going to look like that's my x direction and that's my y direction. And if that's my coordinate system, okay, so it's like this is I kind of drew it out over here. This is my y, and this is my x. The ones that I have on my coordinate system, I have friction. No, lies. I don't have a force there. Friction is the way. Okay. I have friction going this direction. I have normal force going that direction. So that's good and well. I don't have to break up friction normal force. But look at your weight. Your weight is definitely going at an angle according to our coordinate system. And so I need to break up my weight into a component that goes that way and a component that goes that way. So we'll call this WY and we'll call this WX. Now, in terms of, well, how do you know what to break that up on? And I didn't leave a board for this, so I'm going to shift this here and we'll draw it here. If you think about your weight, this is our incline. Here's my angle. If your weight vector, so we have a reference, friction, if weight goes straight down, and I'm saying we're going to break up our weight into components, so one of the components is going to be opposite normal force, we'll call that WY, and one of them is going to be opposite, not opposite anything, but along the x direction. In order to break up any force into components, you need to know what the hypotenuse is, easy, that's our weight, and you need to know an angle. So effectively, we need to know what this angle is. So let me convince you as to the fact that you know what that angle is. If this angle, let's just put a number here, if this angle was, let's make it easy, 30 degrees. And do you see how this is kind of a triangle? Because weight drops straight down. So that means that this right here is 90. And we know that all the angles on a triangle have to add up to 180. So that means that this has to be 60. Well, if that angle is 60, then you should be able to understand that this right here is a 90-degree angle, meaning this angle right here has to be 30 degrees. And so that is a general truth. If you break up weight, and this is for inclines, if you break up weight such that Wy is opposite the normal force. Okay? And our Wy is opposite the normal force. Then that angle, the upper angle, is the angle of the incline. Always, always, always. Okay? Whatever this angle is, that's going to be what that angle is going to be as well. And once you've convinced yourself of it, you shouldn't have to rederive and draw all these triangles. You should just know that that upper angle is whatever the angle of the incline is. So let's just try out an example of this. So here's my example. So it says a block whose mass is 2 kilograms slides down a ramp that has a 50-degree incline. Coefficient of friction is 0.597. What is the normal force? What is the friction? And then what's the acceleration of the block? So I'm just going to draw my force diagram up here, then I'll use this board as my calculation one. So if here's your incline, similar to what we just kind of drew, and we're looking at our forces. It's very similar to what we had drawn before. Our weight is going to be down. Our normal is going to go up. Our friction is going to go off to that direction because we're definitely going to have an acceleration going down. And we know that we should be breaking up our weight into components. So we'll call that Wy, call that Wx, call that W. So remember, our first step is to always draw a force diagram. Oh, you don't have to be quiet, it's fine. If we break up our weight, we know the weight is always equal to mg, right? And so that means, this is where it's a little tricky. If I were to look at knowing the fact that this angle right here, the problem tells me that the incline is 50 degrees. If I look at trying to figure out what my Wx is, look at this. This is a little different than what we've been doing before, but Wx, do you see how Wx is opposite the angle? So if Wx is opposite the angle, then to figure out Wx, it would be the sine, because it's opposite. So Wx would actually be mg sine of 50, and Wy would be mg cosine of 50. So that's a little bit different because we've gotten into the habit of saying things that are going horizontally should have the cosine value and things that are going vertically have the sine value. So on inclined planes, it's a little bit different just because of the angle that we know. So this is my force diagram. This is me breaking up any forces into components. And then our next step would be to write out our force equations. So let's look at our horizontal forces. So horizontally, again, remember our coordinate system is skewed. Our coordinate system is skewed. So this is my y direction and this is my x direction. So horizontally, I have this Wx and I have friction. And so it's Wx minus friction is equal to ma. But let's kind of put in what we know. I know Wx is just equal to mg sine of theta, and I know my equation for friction is mu times normal force, and that's going to equal ma. So that's my horizontal equation. For my vertical equation, I'm going to come down here, I'm going to leave a little bit of space because I know I'm going to have to finish calculating that. For my vertical equation, I look at what's happening vertically, and the two forces I have vertically are this normal force and this Wy. And so I'm going to say, okay, well, normal force minus Wy equals ma. But this object is not moving vertically. It's only going down my ramp. It's only going down horizontally according to my new axes, okay? So I'm not accelerating in that direction. So because I'm not accelerating in that direction, this is equal to 0, okay? Again, this acceleration is equal to 0. This ay is equal to 0 because I am not moving this way on my ramp. Let's go ahead and simplify this to what I know. N is still N, but Wy is mg cosine of my theta, and that's going to equal to 0. So now that I have my equation set up, let's look at what the problem is actually asking for. And the first thing it says is, what is the normal force? And so normal force is actually here and it's here. But in this equation, I don't know normal force and I don't know the acceleration, so I cannot use this equation to find my acceleration. So I've got to come down here and say, oh, well, normal force. If I bring that to their side, normal force is equal to mg cosine of theta. And if I actually plopped my numbers in, this would be 2 times 9.8 times cosine of 50. So go ahead and take a moment to actually calculate that out. Let's see if I get more. So hopefully if you did your math right, you should have gotten 12.6 newtons. So that's your normal force. Next thing asks, what is the friction? And so that's just coming back to our basic equation that friction is equal to mu times normal force. So I've got my mu, it's 0.597. And my normal force I just found is 12.6. So go ahead and calculate out what that value is. And you should have gotten 7.52 newtons. And then the last question is, what is the acceleration of the block? So here's our only equation with acceleration. So we're going to come back here and say, okay, my mass is 2 times gravity of 9.8 times sine of 50 minus mu n. Well, I already calculated mu n, so this is going to be minus 7.52 equals 2 times a. And so we'll calculate out that one final answer for a. And hopefully you got an acceleration of 3.75 meters per second squared. Okay? So we'll definitely do some more examples of this in class, and then I think it's on Tuesday we will do a lab on it.